session on operating systems. Now we are into our third module, where we look at what process synchronization is and what the deadlocks are and how they can be controlled. So the whole story begins that imagine a situation at a cafeteria where multiple customers walk up to get food from the same counter. But what if two customers reach for the same serving spoon at the same time? Yeah. So there are dishes, and the dishes have to be served using these serving spoons, and anytime only one customer can use this serving spoon. But here the situation is two customers are trying to use the same serving spoon at the same time, or even worse than that. What if each holds one serving spoon and refuses to let go until they get the other? Say two dishes are there, and both dishes are required by both the customers. One catches hold of one serving spoon of one dish, and other one the serving spoon of the other dish, until both serve themselves with both the dishes. They are not ready to leave the spot, but to have both, they need both the spoons, and which is currently not possible because each customer is holding one spoon. Then they want both together, only then they can release the one they are holding, and both of them are holding one each other. Therefore it is not possible to continue further. So that's what exactly happens inside a computer also, when multiple processes try to access the shared resources like memory, printers or files without any proper coordination. Welcome to the world of process synchronization, where the operating system ensures that processes don't clash or corrupt data while sharing the resources. But just like in the cafeteria, poor coordination can lead to chaos. Imagine that there are four processes, each waiting for resources that another is holding, and no one is willing to give up. So they are holding one and wanting the other one, and that other one is already held by some other process. So in this case, what happens? They say, I am having this resource, until I get the other one I will not release this resource, because I need both the resources to complete my task, and till I get both the resources I cannot complete my task, and till I complete my task I cannot release the one which I am presently holding. Same story is from all the four processes, and each process holding one, waiting for one more, and this leads to a situation where everyone halts and nothing progresses, and this situation is called a deadlock. So in this series we explore why synchronization is essential among the processes, and what can go wrong if we do not care for synchronizing the processes, and how the operating system uses various tools to prevent such chaos and keep processes running smoothly. So in this part of the series, let us look at the various problems of synchronization, lack of synchronization, and then how the synchronization can be achieved, and how the problem can be solved. So that's what is the whole goal of this module. So friends, get ready, because understanding this part of operating system is like learning the traffic rules of process management. Without them, you end up in a traffic jam. So let's get into more details of what process synchronization is and what deadlocks are and how avoiding these deadlocks. So friends, welcome. I am Dr. Sandeep. Let's get ready to understand topics in detail. So begin our journey with process synchronization. So the whole story begins with cooperating processes, and these cooperating processes which do use shared resources like memory, files, or other I/O devices, and these can affect or may be affected by other processes executing in the system. So the cooperating system can affect another process in the system, or a cooperating process may be affected by other processes executing in the system. And this happens because the resources are either directly shared as a logical address space, that is code and data, or may be allowed to share the data only through files or messages and all that. Whatever we have, so we do have problems, and because of lack of synchronization, we may end up in data inconsistency. And the whole goal of this next few lectures is to ensure the consistency of the data and make sure that everything works smoothly without creating any chaos. So the solution for all this problem is what we call process synchronization. So the objectives of synchronization among the processes is to introduce something called a critical section and find the solutions used to ensure consistency of the shared data. So what is a critical section? That is, a critical section is one where the shared data or the shared resources is being used by one process, or any part of the code that makes use of shared resource we call critical. Because if more than one process try to work with these shared resources, they may create inconsistency. So we want to be very serious while working with such part of a code. Therefore we highlight them a section which we call critical section. And we have to understand how software or hardware solutions are available for these critical section problems, and then to introduce the concept of atomic transaction and describe mechanisms to ensure atomicity. So atomicity is one. That means if we are talking about a critical section, then that critical section has to be completely executed, or none of the lines should be executed. So we are talking about critical section that is usually made up of some multiple lines of code, and if part of the code is executed before preempting and calling some other process, then there is inconsistency problem. So what we need to do is, once a process enters a critical section, we should ensure that none of other processes should be allowed to work with the same critical section. So that means that critical section should be executed in an atomic way. That means either should be completely run or none is run. So we need to find some way out to ensure this atomicity. So let's check what the atomicity problem is, what the synchronization problem is with an example. So the example here we use is a producer consumer problem. So here what we are trying to do is we have two processes, and in the process management earlier we had seen that we don't want to mix up the things, so we keep the things separate, and if at all they want to communicate with each other, then we had two ways to come out. So one we called shared memory and the other one we called message passing. So let's consider the shared memory logic to communicate. So we have one that is a producer that produces some information, and there is another process which is called consumer that consumes that information. So this information produced by the producer should write the information onto the shared memory, which we call a buffer, and this buffer is allowed to be used by both these processors, producer as well as consumer. So the producer produces the information, writes onto the buffer. The consumer has access to this buffer, will read from the buffer and uses it. So producer writes onto the buffer, consumer reads from the buffer, and that way we transfer message from producer to consumer via shared memory. So this code is talking all about that, and we are not much bothered about what the whole code is. So just look at the first line. Says that while the counter is of the buffer size, which means that there is no more space left to write, because the whole buffer is already written and the consumer has not yet read anything, therefore the buffer is complete. So as long as the buffer is complete, we cannot write anything, so we keep waiting there, do nothing. The moment buffer size is less than the actual buffer size, that means some space is made free, that is something is consumed, then we have a space in the buffer, so we write that the next produced information onto the buffer and then increment that. Then we want to keep track of how many data information were written onto the buffer, so for that we have this counter plus plus, so that is what we keep counting. So every time a new item is written onto the buffer, we increment the counter, so we can keep track of how much is written onto the buffer and is there any space left in the buffer and all that. That's what we are looking. As long as the counter is equal to buffer size, we don't have to do anything because there is no space left for writing. So we need to wait till consumer removes at least one information from the buffer. Till then, wait. What happens on the other side? On the other side, yes, same thing happens, but only thing is we have to wait if the buffer is empty. If the buffer is empty, we can't read anything. Then we have to wait till producer writes something onto the buffer. So here we are waiting till counter is 0, just keep waiting. If counter becomes something other than 0, the greater than 0, that means there is something to read. Okay, now the consumer starts working, and once it takes out one information from the buffer, then we should know that the buffer contains one information less, and that is maintained in the counter again. So when we add a new information to the buffer, we incremented the counter, and when we removed one information from the buffer, we decremented the counter. And that's simple common sense problem, right? What is problem in this? Yeah, let's look in detail how this counter plus plus is done and how this counter minus minus is done. So assume that we have at some state the number of information written on the buffer is 5. Then the next step, the counter may have value 4 or 5 or 6. Confused? Yes, of course, should be. But why such thing happens? What is actually happening? We assume that now counter is 5 and producer will produce one item and then consumer will consume one item. So if producer produces one item, then counter should become 5 plus 1, 6. That's what the counter plus plus is saying. And then if the consumer consumes one item, then the 5 had become 6 and 6 should become back to 5 because we are checking of counter minus minus. But there's not always possible. There are chances that the counter value may be 4, maybe 5, maybe 6. Yes, of course, it is confusing. And why? Let us check that. So this is what happens when you say counter plus plus. This counter plus plus is a high level instruction, but at the core the value of the counter should get into some register of the processor, and then register value should be incremented, and this register value should be put back onto the counter. So there is a variable called counter which is there in the main memory or the RAM. So when I say counter plus plus, then the value from that location counter should get into register, and that register value should be incremented, and that incremented value will be written back onto the same position. So if I take up the previous example, counter value was 5. Now 5 comes to register 1. Register 1 gets updated by plus 1, then it becomes 6, and that 6 return back. Looking at another side, the counter minus minus. So that's where the counter value goes into register, the register is decremented and returned back. Now if these two are running concurrently, then at time t0 the producer will execute the first instruction. So 5 goes into register 1, then t1 again producer gets chance, so it gets into the second instruction, then register 1 value goes to 6. Then in the third clock the consumer may start working and it reads the counter value. Counter value is not yet written by the producer, therefore it still reads 5, and at t3 consumer executes the decrement of the value, then register 2 becomes 4, then producer executes writing the register value onto the counter location. So 6 is written at the location counter, and finally the consumer is executing its last line and it writes 4 onto the counter. So what has happened was these two last three lines are updating the counter value, and the counter value first was updated by the producer by 6 and then by the consumer by 4. Therefore finally the value written on the location is 4, and hence the answer is wrong. So if the producer is executing first and the consumer is executing the last two lines, if you look at it, the answer is 4, because producer writes 6 onto the location, then consumer writes 4, so 4 remains finally. If that is done other way, if consumer writes first, it will write 4, then producer writes next, then it will write 6. The value in the counter will be 6. But if they are run separately, not interleaving like this, if all three instructions of producer are run first, then counter will become 6, and all 3 instructions of the consumer are run next, then finally it will become 5. So that is the problem with the shared memory, and multiple processes are trying to use this shared memory. And to solve this, we must ensure that these 3 lines, whether of consumer or the producer, should be called a critical section. That means if the first line begins to execute, then all 3 should execute, or none of the 3 should be executed. That's what we call atomic execution. And because of this, whatever we have seen is what we call race condition. This occurs when 2 or more processes or threads access the shared data concurrently, and the final outcome depends on the timing or the order of the execution. Yeah, that's what race condition is, and this is the major problem which forces us to go for what we call process synchronization. So that's it for now. Thank you.